In this lecture, we're going to accomplish two goals. First, we're going to get to see what we mean by formulating an optimization problem. And after that, it turns out Microsoft Excel has an embedded optimization solver in it. And we're going to see how to use Microsoft Excel's embedded optimization solver to solve relatively small optimization problems. Okay, so that's what we're going to do today. First, we're going to see what we mean by formulating an optimization problem. And after that, Microsoft Excel has an embedded optimization solver in it. We're going to see how we can use Microsoft Excel's optimization solver to solve relatively small optimization problems. Good. And to understand what we mean by formulating an optimization problem, we're going to use a couple of examples. So here's our first example. Okay, here's our example. Let's imagine that we're operating a cloud computing company. We're operating a cloud computing company, and we have 1,000 servers to lease to our users on a daily basis. And there are two types of users that come and lease servers from us: standard users and power users. Each standard user pays $3 per day, and each standard user consumes 1 unit of energy per day. And each power user pays $4 per day, and each power user consumes 2 units of energy per day. And the total energy available per day is 1,600 units. And the question we're interested in is how many servers we should be leasing to standard users and power users so that we maximize the revenue that we collect per day. Okay, so this is the problem that we would like to solve. We have 1,000 servers to lease to our customers. We have two types of customers: standard users and power users. Standard users pay $3 per day and consumes 1 unit of energy per day. Power users pay $4 per day and consume 2 units of energy per day. And we have 1,600 units of energy available per day. And we want to figure out how many servers we should be leasing to standard and power users so that we maximize the total revenue that we collect per day. Okay, so this is the problem that we would like to solve. So we're going to formulate this problem as an optimization problem. And when we say we're going to formulate an optimization problem, we need to specify three things. We need to specify what our decision variables are. We need to specify what our objective function is. And we need to specify what our constraints are. Okay, so formulating an optimization problem means we need to specify what our decision variables are. And then we need to specify what our objective function is. And then we need to specify what our constraints are. Good. So now let's do these three things. First, we need to specify what our decision variables are. Decision variables are the quantities that we adjust to reach our goal. So roughly speaking, decision variables are the quantities that we adjust to reach our goal. What is our goal? Our goal is to maximize the revenue per day. And what are the quantities that we adjust to maximize the revenue per day? The number of servers that we lease to standard users and the number of servers that we lease to power users. Those are the quantities that we can play around with to maximize the revenue that we collect per day. So then what are the quantities that we adjust to maximize the revenue per day? The number of standard users that we lease service to and the number of power users that we lease service to. So those are going to be our decision variables. So let's start with that. Our decision variables in this problem. So one decision variable, let's see, is going to be x sub s, and that's going to be the number of servers leased to standard users. Another decision variable is going to be little x sub p, and that's going to be the number of servers leased to power users. Okay, so those are our decision variables. Good. The next thing we think about is our objective function. Let's think about our objective function. What's our objective? Our objective is to maximize the revenue per day. Our objective is to maximize the revenue per day. So we're going to write the revenue per day as a function of our decision variables. We're going to write down the revenue per day as a function of our decision variables, xs and xp. Each standard user pays $3 per day. Each power user pays $4 per day. So then our revenue per day is given by, these are the number of servers that we lose to standard users. And each one of these standard users is going to bring us $3 per day. And these are the XPs, the number of servers that we lose to power users. And each one of those power users is going to bring us $4 per day. So this is our daily revenue. And we would like to maximize this objective function. Okay, so now we wrote our objective function, which is the revenue per day, as a function of our decision variables, only as a function of our decision variables. So now we specified our objective function. The next thing we think about is how do we specify our constraints? We need to specify our constraints. Constraints are the limits on the decisions that we can take. Constraints are the limits on the decisions that we can take. So for example, how many servers do we lease at our disposal? We have 1,000 servers. So that means that the total number of servers that we lease to standard users and the power users cannot exceed 1,000, right? So now one constraint that we have is that the total number of servers that we lease to standard users and the power users cannot exceed the number of servers that we have, which is 1,000. So then the number of servers that we lease to standard users is XS, and the number of servers that we lease to power users is XP. So this is the total number of servers that we lease to our customers that cannot exceed 1,000. So that is one constraint. Again, we specify all of our constraints by using only our decision variables and only our decision variables and nothing else, okay? And the sign of this constraint is a less than or equal to constraint, meaning that the total number of servers that we lease to the standard and power users is going to be less than or equal to, should be less than or equal to the total number of available servers that we have on hand. What else? What other constraints do we have on our decisions? We do not have infinite amount of energy. We have 1,600 units of energy available to us per day. And the standard and power users are using energy. So let's write down the energy consumption by the standard and the power users. Each standard user consumes 1 unit of energy. So these are the number of servers to lease to standard users. So each one of these guys is going to consume 1 unit of energy. So that's the energy consumption by the standard users. And these are the number of servers leased to power users, XP. And each one of the power users is going to consume 2 units of energy. So now this is the total amount of energy that we use per day, and that should be no larger than the amount of energy that we have available per day. That's 1,600. So that's the second constraint that we have. And also we want the number of servers that leads to power users and the standard users to be non-negative. That's another constraint as a non-negative constraint on our decision variables. Okay. So then we more or less specified our optimization problem. We identified our decision variables, and then we wrote our objective function as a function of our decision variables. And then we listed a list of constraints that limit our actions, again, only as a function of our decision variables, okay? Good. And these constraints that we have in this problem were of the less than or equal to form, but in another kind of an optimization problem, you can have a greater or equal to constraint, you can have an equality constraint, and so on and so forth. Right now, we're saying that the total number of servers we use should be less than or equal to the number of servers we have available, and the total amount of energy that we use should be less than or equal to the amount of energy that we have available. Okay, good. And here we have xs and xp greater or equal to 0 constraints. So then if we want to put all of these things together to write down what an optimization problem looks like, so here's what an optimization problem looks like. Here's what an optimization problem looks like. We maximize the objective function subject to these constraints. This ST means subject to. Maximize this objective function subject to these constraints. So this is what it means to formulate an optimization problem. Identify the decision variables and write down the objective function, and then write down a list of constraints. And our optimization problem is maximize this objective function subject to a list of constraints. And once again, last time, our objective function and all of our constraints are only specified as the functions of our decision variables. Good. Okay. So this is what we mean by formulating an optimization problem. And this optimization problem is a special optimization problem in the sense that the objective function is a linear function of the decision variables. It's just the decision variables multiplied by constants added all up. Likewise, the right-hand side of these constraints are linear functions of the decision variables. Each one of these decision variables multiplied by constants added all up. Each one of decision variables multiplied by constants added all up. Again, this is one of my decision variable multiplied by constant 1. This one of my decision variable multiplied by constant 1. So this is an optimization problem where the objective function and all of the left-hand side of the constraints are linear functions of the decision variables. So we call these kinds of optimization problems where the objective function and all of the constraints are linear functions of decision variables as linear programs. And for the majority of this course, we're going to be interested in solving linear programs. We're going to be focused on optimization problems where the objective function and all of the constraints are linear functions of the decision variables. For a majority of this course, we're going to be dealing with linear programs. optimization problems where the objective function and all of the constraints are linear functions of the decision variables. Good. So now I would like to solve this optimization problem. I want to find a value of xs and xp that maximizes the objective function while making sure that the values of xs and xp satisfy all of these constraints. Good. So now let's write down some terminologies. The first terminology I would like to introduce is the notion of a feasible solution. A feasible solution. An excess XP pair that satisfies all of the constraints in my linear program, an excess XP pair that satisfies all of the constraints in my linear program is called a feasible solution. Let's say it again. An excess XP pair that satisfies all of the constraints in our linear program is called a feasible solution. Let's give an example of a feasible solution. For example, xs and xp given by, let's say, 200 and 500. xs and xp given by 200 and 500. x is equal to 400 and xp is equal to 500. Does this xs xp pair satisfy all of the constraints? X is equal to 200, xp is equal to 500, 200 plus 500, 700, 700 is less than or equal to 1000. So this solution satisfies the first constraint. xs plus 2xp, xs is 200, xp is 500, xs plus 2xp is 200 plus 2 times 500, 200 plus 1000 is 1200, 1200 is less than or equal to 1600, so this solution satisfies the second constraint as well. Xs is 200 greater than or equal to 0, xp is 500 greater than or equal to 0, so indeed this is a feasible solution to our linear program. So this solution is a feasible solution to the linear program. And let's look at the objective value provided by the solution. What is the objective value provided by the solution? Xs is 200, xp is equal to 500. 3 times 200 is 600. 4 times 500 is 2000. So the objective value provided by the solution is 2600. Okay, xs, xp, 200, 500 is a feasible solution to LP, providing the objective value of 3 times 200 plus 4 times 500, that is 2600. Good. So that's what it means. That's what we mean by a feasible solution. A pair of decision variables that satisfies all of the constraints is a feasible solution to our linear program. Okay. On the other hand, what is an optimal solution? What is an optimal solution? A feasible solution that gives us a better objective value than any other feasible solution is the optimal solution. Okay, a feasible solution that gives us an objective value that is better than any other feasible solution is the optimal solution. So among all the xs xp pairs that satisfies all of the constraints, the xs xp pair that gives us largest objective value is going to be the optimal solution. So an xxp pair, among all the feasible XSXP pairs, the one that gives us the largest possible objective value is the optimal solution. And when we solve an optimization problem, we're interested in identifying the optimal solution among all the feasible solutions, which is the one that gives us the largest possible objective value. Okay, good. So today we're going to see how we can use Microsoft Excel's embedded optimization solver to solve this optimization problem. And starting in the next lecture, we're going to develop algorithms that actually solve these kinds of optimization problems. But today we're just going to see how to use Microsoft Excel's optimization solver to solve this kind of an optimization problem. Here's how we're going to do it. Bring up an Excel spreadsheet. Okay. We're going to reserve 2 cells to store our decision variables. So we have 2 decision variables. Let me name these cells xs and xp. And I'm going to use cell A2 to store the value of the decision variable xs. And I'm going to store xp to store the value. I'm going to use the cell A2 to store the value of the decision variable xs. And I'm going to use cell B2 to store the value of the decision variable xp. For now, let's put some bogus values there. Okay, good. Excel solver is going to find the values of these decision variables to make the objective function as large as possible while making sure that we satisfy our constraints. The next thing we're going to do is we're going to write a formula that keeps track of our objective function. Next thing we're going to do is we're going to write a formula that keeps track of our objective function. What's our objective function? 3xs plus 4xp. 3xs plus 4xp is our objective function. So now let's write our objective function. 3 times xs the value of xs is included in cell A2, plus 4 times xp. The value of decision variable xp is included in cell B2. So now in cell A3, we have a formula that keeps track of our objective function. So this is our objective function. Similarly, we're going to write constraints that keep track of our constraints. What's the left-hand side of our first constraint? xs plus xp, xs plus xp. So let's write a formula that keeps track of the left-hand side of the first constraint, xs plus xp. Good, xs plus xp, a2 plus b2. So then the cell A4 is keeping track of the left-hand side of the first constraint. And what is our second constraint? What is left-hand side of our second constraint? xs plus 2xp, xs plus 2xp. xs plus 2 times xp. Okay, so that's the formula that keeps track of the left-hand side of the second constraint. Great. And we have these non-negativity constraints. It turns out Excel solver can take care of non-negativity constraints automatically, which we're going to see in a minute. So we're not going to explicitly write the non-negativity constraints. So now we prepared our spreadsheet. We prepared our spreadsheet in the sense that we have two cells that is keeping track of our two decision variables. We have a formula that keeps track of our objective function as a function of our decision variables. And we have a formula that keeps track of the left-hand side of the first constraint as a function of our decision variables. And we have a formula that keeps track of the left-hand side of the second constraint as a function of our decision variables. Okay, good. And my notation here, these signs is just only meant to say that this is pointing to our objective. This is pointing to the first constraint. That's just a pointer. This is pointing to the second constraint. Good. So now let's go to Excel solver. Excel solver is underneath tools and solver right over here. And if somehow Excel solver is not appearing under the tools menu, you can go to Excel add-ins and add Excel solver by clicking this checkbox. I already did that, so my Excel solver is appearing under the tools menu. Let's go to solver. Okay. So now it says set the objective, set objective. Where is our objective formula? Our objective formula is in cell A3. There we go. Do you want to maximize the objective? Do you want to minimize the objective? Or do you want to change the values of our decision variable such that the objective exactly takes a particular value? You want to maximize our objective. So we click this radio button, all good. By changing variable cells. So this is going to be where we specify our decision variables. By changing variable cells, A2 and B2. So we're going to drag across A2 and B2. So those are going to be our decision variables. And lastly, subject to the constraints, we're going to add some constraints now. We're going to add some constraints. Let's say add. Good. Our first constraint was xs plus xp is less than or equal to 1000. Our first constraint was xs plus xp is less than or equal to 1000. Let's go to my Excel. In this cell, A4, we had the value of xs plus xp. We had the formula for xs plus xp, and we want that to be less than or equal to 1000. Let's say add, we added the first constraint. What is our second constraint? Our second constraint was xs plus 2xp is less than or equal to 1600. And this cell A5, we had xs plus 2xp less than or equal to 1600. And we can use all sorts of other constraints. We can say our constraints are going to be something is less than or equal to a number, something equal to a number, something is greater than or equal to a number. We can specify certain decision variables to be integers or binaries, but let's not worry about them for now. Right now, we're going to use these two types of constraints. We can have less than or equal to constraint, equal to constraint, or greater than or equal to constraint. So far, our constraints are all less than or equal to constraint. Add this constraint as well. We added all of our constraints. Let's say cancel to get out of this. So then our solver looks like this. Our objective function is included in cell A3. We're maximizing that objective function. Our decision variables are in cells A2 to B2. And our constraints are A4 is less than or equal to 1000, and A5 is less than or equal to 1600. And there is this checkbox here that says make unconstrained variables non-negative. So since this checkbox is checked, automatically all of decision variables are going to be constrained to be non-negative. Okay. And over here, we have a select a solving method. If you have a linear optimization problem where our objective function, all of the constraints are linear in our decision variables, the algorithm that we need to check is the simplex LP. So this is a good, robust algorithm for solving linear optimization problems. Good. So now we're going to say solve. We're going to click solve. And once we click solve, Excel solver is going to adjust the values of our decision variables included in cells A2 and B2 to maximize our objective function while adhering to our constraints. So let's click solve, and what's going to happen? Let's see what's going to happen. Solver came back to us and said, solver found a solution. All constraints and optimality conditions are satisfied. Keep the solver solution. I'm going to keep the values of the cells A2 and B2 that have been adjusted by the solver. So that is the solution that we get. Let's say, okay. So now what we got here is that the optimal solution to this problem is xs is equal to 400, xp is equal to 600, and the corresponding objective value is 3600 apparently. Okay. But x is equal to 400, xp is equal to 600 is the optimal solution. Let's write that down. So the optimal solution, x is equal to 400, xp is equal to 600, right over here, 400, 600, is the optimal solution to our LP. Providing the objective value, providing, let's say, the optimal objective value. Three times 400, 4 times 600. This is 2400, another 1200, 3600. And not surprisingly, in our Excel spreadsheet, our objective function value relates to 3600, which is the value of the objective function related to these values. Okay. Good. And is the solution feasible to our linear program? XS plus XP, 400 plus 600 is 1000. It's indeed less than or equal to 1000. XS plus 2XP, 400 plus 2 times 600, 400 times 1200, it's 1600. It's indeed less than 1600. So it's satisfying all of the constraints. Good. One thing to emphasize is that in a linear program, in an optimal solution, the values of our decision variables can take on fractional values. So we could be solving this optimization problem, and Excel solver could come back to us and say that the optimal values of XS would be 344.667894, and the optimal value of XP is 400.2486785535. Okay, so the optimal solution to a linear program can take fraction values. The fact that the optimal solutions of XS and XP came out to be integers here is by pure luck. Okay, and for the majority of our course, we're going to deal with optimization problems. We're going to deal with linear programs, which means that an optimal solution to that linear program can take fractional values. But if you're dealing with large quantities, like 400-ish, 600-ish, well, if the optimal solution is 400.005876, you can round it down. If the optimal solution is 625.889354, you can round it down. But towards the end of the semester, towards the end of the lectures, we're going to start specifically study optimization problems where decision variables are restricted to be integers. It turns out solving optimization problems where decision variables are restricted to be integers is going to be a lot harder, but nevertheless, we're also going to deal with optimization problems where decision variables are restricted to be integers, but that is going to come way later. For now, when we write a linear program, we understand that in an optimal solution, the optimal values of our decision variables can take fractional values, and that's something we have to live with. Okay, good. So that is what we mean by formulating an optimization problem. Specify decision variables, write the objective function and all of the constraints only as functions of our decision variables. Throughout the semester, we're going to be dealing with linear programs. Linear programs are optimization problems where the objective function and the left-hand side of our constraints are all linear functions of the decision variables. A feasible solution is an XS-XP pair that satisfies all of the constraints. And an optimal solution is a feasible solution that gives us a better objective value than any other feasible solution. Okay, that gives us the best. An optimal solution is a feasible solution that gives us the best possible objective value. And we saw how we can use Excel to solve this kind of an optimization problem. We saw how we can use Excel solver to solve this kind of an optimization problem. Okay, so now let's look at a little bit of a larger example. Again, to go through the exercise of identifying the decision variables and writing down the objective function and the constraints. But this example, again, is going to be a little bit larger, a little bit more interesting. Here's the second example we're going to look at. So let's say we're running a website. On our website, there are three advertisers called advertiser A, B, and C that are running ads on our website. So let's say advertiser A is Nike, advertiser B is Adidas, advertiser C is Camper. Okay, so we have three advertisers A, B, and C who are running ads on our website. And advertiser A would like its ads be seen by 2,000 viewers. Advertiser B would like its ads be seen by 3,000 viewers, and advertiser C would like its ads be seen by 1,000 viewers. So these are the desired number of viewers by each one of the advertisers. Advertiser A would like its ads be seen by 2,000 viewers. Advertiser B would like its ads be seen by 3,000 viewers. Advertiser C would like its ads be seen by 1,000 people. And there are three types of visitors, indexed by 1, 2, 3, that come and visit our websites. And these three types of visitors correspond to visitors in different age ranges. So visitors of type 1 are the younger visitors. Visitors of type 2 are middle-aged visitors. And visitors of type 3 are elderly visitors. Okay, we have three types of visitors that are coming, visiting our website. Again, visitors of type 1, type 2, type 3. Type 1 visitors are younger, type 2 visitors are middle-aged, type 3 visitors are elderly. And then daily numbers of visitors of each type are given by these numbers. So you have 1,500 visitors of type 1 coming into our website, 200 visitors of type 2 coming onto our website daily, and 2,500 visitors of type 3 coming to our website. And if we display an ad from a certain advertiser to a visitor of a certain type, then we generate a revenue that depends on the advertiser itself and the type of the visitor. And those revenues are given over here. For example, if a visitor of type 2 is shown an ad from advertiser B, we make 1 cent. If a visitor of type 3 is shown an ad from advertiser A, we make 1.5 cents. If a visitor of type 1 is shown an ad from advertiser C, we make 2.5 cents. Okay, when we show an ad to a visitor of a certain type from a particular advertiser, we make a revenue, and those revenues depends on the type of the visitor and the advertiser, and those revenues are given by this table. And the question we're interested in is, how many ads do we display to visitors of each type from each advertiser so that we maximize the revenue per day? Okay, and we're going to assume that each visitor can see one ad. Each visitor can see one ad. Okay, good. All right. So again, we have three advertisers: A, B, C, Nike, Adidas, Camper. And advertiser A, B, C would like their ads be seen by 2,000 people, 3,000 people, 1,000 people. These are the desired number of viewers by each advertiser. We have three types of visitors, indexed by 1, 2, 3. Visitors of type 1 is young, visitors of type 2 is middle-aged, visitors of type 3 is older. And data numbers of visitors of type 1, 2, and 3 are 1,500, 2,000, and 2,500. And whenever we show an ad to a visitor of a certain type from a certain advertiser, we make a certain amount of revenue, and that's tabulated in this table. We want to figure out how many ads we display to visitors of each type from each advertiser so that we maximize the revenue that we collect per day. So this is the problem that we would like to formulate as an optimization problem. Good. Once again, we're going to go through the exercise of specifying what the decision variables are, writing our objective function, and writing our constraints. So what are the decision variables? What are the decision variables? We have three types of visitors, and we have three advertisers. We need to think about how many visitors of each type is seeing an ad from each advertiser. Let's see it again. We want to think about how many visitors of each type is seeing an ad from each advertiser. Okay, so then our decision variables are going to be like, let's say x1a, x1, x subscript 1a, x subscript 1a, number of visitors of type 1 shown an ad from advertiser A. Likewise, we have x1b. It's going to be the number of visitors of type 1 shown an ad from advertiser B. Okay, and similarly, what do we have? We have x1c, which is number of visitors of type 1 shown an ad from advertiser C. And likewise, we have x2a, number of visitors of type 2 shown an ad from advertiser A. We have x2b, number of visitors of type 2 shown an ad from advertiser B. X2C, number of visitors of type 2 shown in ad from advertiser C. X3A, number of visitors of type 3 shown in ad from advertiser A. X3B, X3C, let's say similarly. Good. How many decision variables do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a problem with 9 decision variables. Great. So next thing we do is we specify our objective function. We write down our objective function. Each visitor of type 1 seeing an ad from advertiser A is bringing us 1.5 cents. Each visitor of type 1 seeing an ad from advertiser A is bringing us 1.5 cents. So we have X1A visitors of type 1 seeing an ad from advertiser A, and each one of those people is going to bring us 1.5 cents. So that is revenue that we collect from visitors of type 1 seeing an ad from advertiser A. And likewise, we have X1B number of visitors of type 1 seeing an ad from advertiser B, and each one of these visitors, each one of these shows is going to give us 3.5 cents. That's revenue that we collect by showing ads to visitors of type 1 from advertiser B. X1C, visitors of type 1 seeing an ad from advertiser C. Each one of these is making us 2.5 cents. Visitors of type 2 seeing an ad from advertiser A. Each one of them is giving us 2 cents. Visitors of type 2 seeing an ad from advertiser B. Each one of them is bringing us 1 cent. And 3 cents for visitors of type 2 seeing an ad from advertiser C. Let's keep going. 1.5 cents for visitors of type 3 seeing an ad from advertiser A. 4 cents visitors of type 3 seeing an ad from advertiser B. And 2 cents visitors of type 3 seeing an ad from advertiser C. So that is the objective function that we have, and we would like to maximize that objective function. What are our constraints? What are our constraints? Okay. We do not have infinite number of visitors. We do not have infinite number of visitors. So for example, daily visitors of type 1 we have is 1,500. Daily visitors of type 1 is 1,500. That means that the total number of visitors of type 1 that are seeing an ad from any of the advertisers should be no more than 1,500. Let's see it again. We have 1,500 visitors of type 1 coming in. We have 1,500 visitors of type 1 coming in. We have 1,500 visitors of type 1 coming in. So that means that the total number of visitors of type 1 who are seeing an ad from any of the advertisers can be at most 1,500. Total number of visitors of type 1 who are seeing an ad from any of the advertisers can be at most 1,500. How are we going to write this constraint? How are we going to write that constraint? X1 is the number of visitors of type 1 seeing an ad from advertiser A. X1B is the number of visitors of type 1 seeing an ad from advertiser B. X1C is the number of visitors of type 1 seeing an ad from advertiser C. So this sum is the number of visitors of type 1 seeing an ad from advertiser A, number of visitors of type 1 seeing an ad from advertiser B, number of visitors of type 1 seeing an ad from advertiser C. So this is the total number of visitors of type 1 seeing an ad from any of the advertisers. So the total number of visitors of type 1 seeing an ad from any of the advertisers can be no more than the total number of visitors of type 1 that we have coming in, and the total number of visitors of type 1 coming in is 1,500. Right over here. And we're going to write a similar constraint for visitors of type 2. Daily number of visitors of type 2 is 2,000. Daily number of visitors of type 2 is 2,000. So then X2A is the number of visitors of type 2 seeing an ad from advertiser A. X2B, number of visitors of type 2 seeing an ad from advertiser B. X2C is the number of visitors of type 2 seeing an ad from advertiser C. So this sum is the number of visitors of type 2 seeing an ad from advertiser A, number of visitors of type 2 seeing an ad from advertiser B, number of visitors of type 2 seeing an ad from advertiser C. So this sum is the total number of visitors of type 2 seeing an ad from an advertiser that can be no larger than the total number of visitors of type 2 coming in. And lastly, what is the daily number of visitors of type 3? That is 2,500. Let's write a similar constraint for that. Number of visitors of type 3 seeing an ad from advertiser A, number of visitors of type 3 seeing an ad from advertiser B, number of visitors of type 3 seeing an ad from advertiser C. This is the total number of visitors of type 3 seeing an ad from any of the advertisers. That should be no larger than the daily number of visitors of type 3, and daily number of visitors of type 3 is 2,500, right over here. Good. So that is one type of constraint that we need. That is one type of constraint that we need. What else? Each one of these advertisers has desired number of viewers. Each one of these advertisers has desired number of viewers. Advertiser A would like to get a total of 2,000 viewers. Advertiser B would like to get a total of 3,000 viewers. Advertiser C would like to get a total of 1,000 viewers. Okay, so now we got to make sure that advertiser A, from all of the visitor types, should be getting 2,000 viewers. Okay, advertiser A, from all of the visitor types, should be getting a total of 2,000 viewers. So in X1A is the number of visitors of type 1 seeing an ad from advertiser A. X2A is the number of visitors of type 2 seeing an ad from advertiser A. And X3A is the number of visitors of type 3 seeing an ad from advertiser A. So this is the number of total number of visitors of any kind seeing an ad from advertiser A. So this is the total number of visitors that advertiser A is getting. That should equal the desired number of viewers that the advertiser has. Okay. Good. Let's also take care of advertiser B. Advertiser B would like to get a total of 3,000 viewers. So among all the visitor types, over all the visitor types, advertiser B should be getting 3,000 viewers. X1B is the number of visitors of type 1 seeing an ad from advertiser B. X2B is the number of visitors of type 2 seeing an ad from advertiser B. X3B is the number of visitors of type 3 seeing an ad from advertiser B. So this sum is the total visitors of any type seeing an ad from advertiser B. So the total number of visitors that advertiser B is getting should be 3,000. And the desired number of viewers for advertiser C is 1,000. Let's take care of that. Number of visitors of type 1 seeing an ad from advertiser C, type 2 seeing an ad from advertiser C, type 3 seeing an ad from advertiser C. That should be equal to the desired number of viewers by advertiser C. And all of our decision variables are non-negative. So let me just write all the decision variables. Okay, so now an optimization problem is maximize the subjective function subject to these constraints. We have 6 of these constraints, and we also have non-negative constraints on our decision variables. Okay, good. So now let's insert this. Let's input this. Let's solve this optimization problem by using Excel solver. And as we do that, we're going to see a few other cute tricks when we're using Excel solver to solve an optimization problem. So it's not going to be a complete repetition of what we just did in the other example. So we're going to learn a few other cute tricks. Okay, let's bring up Excel. Let's open a new sheet. Let's reserve some cells for our decision variables. X1A, X1B, up, X1B, X1C, X2A, X2B, X2C, X3A, X3B, X3C. Those are our decision variables. So these cells, row 2, A2, B2, C2, all the way to I2 is going to keep track of our decision variables. For now, let's put some bogus values there. Actually, you could leave them blank, but that's fine. Let's put some bogus values there. Okay. So these are our decision variables now, values of our decision variables. Solver is going to, when we say solve, solver is going to adjust the values of those decision variables. Okay. So now the next thing we're going to do is we're going to write a formula for our objective function. Okay. And it is 1.5 times x1a, 3.5 times x1b, 2.5 times x1c, and so on and so forth. Writing this humongous formula is going to get somewhat tedious. So here's how we're going to write this formula in Excel. Let me do this if I can. Here's our objective function. Here's our objective function. So to write down our objective function, we're going to put the coefficients of x1a, x1b, x1c in the third row. So the coefficient of x1 is 1.5. Coefficient of x1b is 3.5. Coefficient of x2c is 2.5. Coefficient of x2a is 2. 1 over here, x2b. 3 over here is x2c. 3s has a coefficient of 1.5 in the objective function. 3b has a coefficient of 4 in the objective function. And 3c has a coefficient of 2 in the objective function. Good. So now, row 2 is keeping track of our decision variables. And row 3 is keeping track of the coefficients of these decision variables in the objective function. So if I want to compute my objective function, what I'm going to do is this value times this coefficient, 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 and so on and so forth, this value times this coefficient, all added all up, Okay, and there's a simple way to do that. In Excel, the formula sum product takes two vectors. In Excel, the formula sum product takes two vectors, multiplies the corresponding components, and adds it all up. Okay, so then if I want to take these numbers in row 2 and these numbers in row 3, multiply the corresponding ones and add them all up, I'm going to use the sum product formula for it. Take these values, and I'm going to pull these formulas in a second, so I'm going to let me anchor them by using the dollars here. I'm going to multiply them with the corresponding coefficients here and add them up. Okay? So now the column G is keeping track of our objective function. And it's doing nothing more than taking the values of our decision variables, multiplying them by the corresponding coefficient of the objective function, adding them all up. So it's a nice, convenient way of specifying the objective function. Okay. So now let's think about specifying the constraint. These are our constraints. These are our constraints. Let me focus on the first constraint. What is the first constraint? In the first constraint, the decision variable x1a, x1b, and x1c all appear with a coefficient of 1, and the other decision variables appear with a coefficient of 0. They just don't appear. So in order to be able to write our constraint also in a simple fashion, a compact fashion, when I'm writing our first constraint, we're going to say x1 in the first constraint appears with a coefficient of 1, x1b in the first constraint appears with a coefficient of 1, x1c in the first constraint appears with a coefficient of 1, and the others appear with a coefficient of 0. So then when we're computing the left-hand side of this first constraint, what we're going to do is we're going to take the values of our decision variables, multiply them against these corresponding coefficients, and add them up. That is going to be 1 times x1a plus 1 times x1b plus 1 times x1c, and 0 times the other. That is going to compute exactly the left-hand side of the first constraint. Okay. So now we know how to multiply this vector with this vector. We know how to multiply one vector with the other with the corresponding entries and add them up. That's going to be the sum product formula. And I already have the sum product formula here. Let me copy it down. There we go. Sum product, these coefficients with my decision variables, add them all up. So this is going to be the left-hand side of the first constraint. Okay. To remind myself, let me say that this is less than or equal to constraint. And the right-hand side of this constraint is 1500. Right-hand side of this constraint is 1500. Good. And this is just reminding. This is just what's happening in columns K and L is just a reminder for myself. Okay. Let's write the second constraint. The second constraint. x2a appears with a coefficient of 1, x2b appears with a coefficient of 1, x2c appears with a coefficient of 1. x2 appears with a coefficient of 1. x2 appears with a coefficient of 1, x2b appears with a coefficient of 1, x2c appears with a coefficient of 1, and all the other decision variables have coefficients of 0. There we go. So now these are the coefficients of my decision variables in the second constraint. Take these coefficients, multiply them with the corresponding decision variable values, add them up. That's going to be the left-hand side of the second constraint. There we go. Take these coefficients, multiply them with the decision variables, add them up with the sum product formula. And again, just remind myself, this was also a less than or equal to constraint, with the right-hand side being 2000. This is my second constraint. Let's also write down our third constraint. In our third constraint, x3a, x3b, and x3c. In our third constraint, x3a, x3b, and x3c appears all with a coefficient of 1. x3a, x3b, x3c appears with a coefficient of 1, and 0 in everywhere else. Okay. Let's take the sum product formula right over here. And this is again to remind myself, this is less than or equal to constraint, and the right-hand side of this constraint is 2500. Wonderful. Good. So now we enter the left-hand side of these constraints. And also as a reminder, we reminded ourselves that these are less than constraints in our Excel spreadsheet, and we also put down the right-hand side of these constraints. Okay. So now we're going to start inputting this fourth constraint. And in this constraint, x1a, x2a, and x3a takes coefficients of 1. In this constraint, x1a, x2a, and x3a appear all with coefficients of 1, and no other decision variable appears in this fourth constraint. So in here, x1a, x2a, and x3a appears with a coefficient of 1. Okay. And actually, instead of like, if you don't want to put the zeros explicit, if you don't put any entries, Excel is going to interpret those entries as if you leave some entries empty, Excel is going to interpret those empty entries as 0 as well. So let's not write the zeros explicitly. So now to write down the left-hand side of the fourth constraint, x1a plus x2a plus x3a. So these coefficient times the decision variable values, you sum product them. That is the left-hand side of the fourth constraint. And the fourth constraint is an equality constraint. And the right-hand side of the fourth constraint is 2000. Good. Let's also write the fifth constraint. Fifth constraint is x1b, x2b, x3b equals 3000. x1b, x2b, x3b. Let's take the sum product formula. It's taking those coefficients, multiplying them with the decision variables, adding them all up. And it's an equality constraint. And the right-hand side of this fifth constraint is 3000, right over here. And the last constraint is x1c, x2c, x3c, and the right-hand side is 1000. x1c, x2c, x3c. Let's sum product those coefficients with the decision values. And that's an equality constraint. And the right-hand side of the last constraint is 1000. Okay. Just so that we're consistent, let me get rid of these coefficients of zeros in my constraint coefficients. Because at this point, we know that if I do not put a coefficient, it's interpreted as 0 by Excel anyway. Okay, good. So then, these cells are our decision variables. This cell is keeping track of our objective, and these cells are not keeping track of the left-hand side of our 6 constraints. Good. So now let's go to solving this optimization problem. Tools, solver. Let's go here. Set objective. Our objective is in cell J3. There we go. J3. You want to maximize this objective by changing variable cells. Our decision variables are in cells A2 to I2. So I drag the cells A2 to I2. There we go. Those are our decision variables. So now we're going to add constraints. We're going to learn something cute here. We're going to learn something cute and useful. So in my first set of constraints, the left-hand side, in my first set of three constraints, the left-hand side is less than or equal to right-hand side, the left-hand side is less than or equal to right-hand side, the left-hand side is less than or equal to right-hand side. So all of these are less than or equal to constraint. So in Excel, there's a quick way of entering those constraints. Here are the left-hand side of the first three constraints, and they're all less than or equal to constraints. So I'm going to drag the left-hand side of the first three constraints. And those are less than or equal to constraints. So keep these at less than or equal to. And the right-hand side of these constraints are over here. Okay. So I can specify my constraints in block form. These numbers, these three cells, which are including the left-hand side of the first three constraints, are less than or equal to these three cells, which are the right-hand side of the first three constraints. These guys are less than or equal to these guys. So I specified my constraints in block form. This is something that we hadn't seen before. Let's say add. And likewise, if you look at our last three constraints, the left-hand sides are exactly equal to these right-hand sides. So the last three constraints are equality constraints. So that we can enter those constraints in block form as well. These three cells are the left-hand side of the last three constraints. And we want them to be equal to the right-hand side of the last three constraints. And again, let's add them. Let's say cancel. So then here are our constraints. J4 to J6 is less than or equal to L4 to L6, and J7 to J9 are less than or equal to L7 to L9. So these are our constraints written in block form. That sometimes comes in handy when you have a block of less than or equal to constraints altogether. So you can specify all the right-hand sides in a cell block. So you can specify your constraints in block form. Okay, make unconstrained variables non-negative. So we want to make sure that all of our decision variables are non-negative. We're solving a linear program. So let's use this algorithm called simplex linear program. And now let's say solve. Let's see what the optimal solution we get is. Okay. The cells have been adjusted to these values. The decision variables have been adjusted to these values. Solver found the solutions, and all constraints and optimality conditions are satisfied. Let's keep the solver solution. Let's keep these cells in the adjusted values. So the optimal objective value is 18,250, and this is the optimal solution. meaning that in the optimal solution, 1,500 viewers of type 1 see an ad from advertiser B, 1,000 viewers of type 1 seeing an ad from advertiser C, 2,000 viewers of type 2 seeing an ad from advertiser A, and 2,500 viewers of 2,500 viewers of type 3 see an ad from advertiser B. Okay, all right. So 2,000 viewers of type 2 seeing an ad from advertiser A, 500 viewers of type 1 seeing an ad from advertiser B, and you get the idea. So this is the optimal solution. Good. So this is a little bit more interesting example in the sense that, the decision variables are richer. They're specified by two indices, visitor type index and advertiser index, and the constraints was maybe a little bit trickier to write. Good. Let's come back to our formulation. If you look at this formulation, we had 9 decision variables and we had 6 constraints. And this linear program, by no means, when you compare to the linear programs that we're going to solve in practice, this linear program is a very small linear program. But even for such a small linear program, with 9 decision variables and 6 constraints, writing all of these constraints and decision variables and the objective function one by one explicitly can get quite tedious. And imagine dealing with a decision variable with 10,000 decision. Imagine dealing with a linear program with 10,000 decision variables and 20,000 constraints. Then obviously writing all of the constraints and all of the objective function, all of the constraints, all of the decision variables one by one is going to be humongously tedious. So the next thing we're going to think about is, there are compact ways of writing linear programs. Let's now think about how we can write our linear program, this linear program, in a compact fashion. Okay. And again, that is useful when we're dealing with a linear program with hundreds of thousands of decision variables, hundreds of thousands of constraints, when we're dealing with such a large linear program. And of course, we cannot write that linear program as maximize this objective function with all these decision variables, and subject to all of these constraints. You cannot write all of these constraints explicitly. So now let's think about how we can write linear programs in compact notation. Let's say a compact way of writing linear programs. If we're going to write a linear program in a compact fashion, let's say compact way of writing linear programs. If we're going to write a linear program in compact fashion, the first thing that we need to think about is what is the data for our linear program and how can we represent the data for our linear program in a compact fashion. Let's first think about what is the data for our linear program and how can we represent the data for our linear program in a compact fashion. Good. So what is the data for our linear program? What are the data for my linear program? One piece of data is the desired number of viewers by each advertiser, desired number of viewers by advertiser A, desired number of viewers by advertiser B, and desired number of viewers by advertiser C. So that is one piece of data. What is the other piece of data? Data number of visitors of each type. Visitors of type 1, visitors of type 2, visitors of type 3. Data number of visitors of each type. What else? What other piece of data do we have? Revenue from showing an ad to a visitors of each type to a visitor of each type from each advertiser. So those are also our data. Okay, so we have 3 types of data in our linear program. These revenues, revenue from showing a visitor of a certain type, an ad from a certain advertiser, and also desired number of viewers by each advertiser, and also data number of visitors of each type. So now let's write our data in compact form. So one form of data is, let's say, Rij. Rij is the revenue from showing an ad to a visitor of type 1 from advertiser J. Revenue from showing an ad to a visitor of type I from advertiser J. Revenue from showing an ad to a visitor of type I from advertiser J. Type I from advertiser J. Okay. So, and I is going to range from over the visitor types, 1, 2, 3, and G is going to range over the advertisers, A, B, C. Okay, so that's one piece of data. Good. What else? We have daily number of visitors of each type, 15, 2,000, 2,500. So let's have another piece of data. Let's say VI is the daily number of visitors of type I. And I is going to range over the type of the visitors, 1, 2, 3. And what is our last piece of data? Desired number of viewers by each advertiser. And let's say DJ is going to be the desired number of viewers by advertiser J. And as you realize, we use this subscript I, we reserve the subscript I for a visitor type, and we reserve the subscript J for an advertiser. Again, RIG is the revenue from showing a visitor of type I, showing an ad. Revenue from showing an ad to a visitor of type I from advertiser J, RIJ. VI is the number of visitors of type I, and DJ is the desired number of viewers by advertiser J. Again, we reserve the subscript I for a visitor type, and we reserve the subscript J for an advertiser. Like, for example, let's give some examples. What is R1A? R1A is the revenue from showing an ad to a visitor of type 1 from advertiser A. Revenue from showing an ad to a visitor of type 1 from advertiser A, that's 1.5. What is R2C? R2C is the revenue from showing an ad to a visitor of type 2 from advertiser C. Revenue from showing an ad to a visitor of type 2 from advertiser C, that is 3 cents. Good. What is V1? V1 is the number of visitors of type 1. What is the data number of visitors of type 1? Data number of visitors of type 1, number of visitors of type 1, number of visitors of type 1 is 1,500. What is V3? V3 is the number of visitors of type 3, that is 2,500. What is VA? That's desired number of viewers by advertiser A. What is the desired number of viewers by advertiser A? 2,000. You get the idea. So we specify the data for our problem in compact fashion. RIJs are the revenues, VI is the number of visitors of type I, and DJ is the desired number of viewers by advertiser J. The next thing we do is we specify our decision variables, also in compact fashion. Okay, let's specify our decision variable in compact fashion. And we're going to use the decision variable, let's say X sub ij. X sub ij is going to be the number of viewers of type I seeing an ad from advertiser J. Let's say number of visitors of type I, or number of viewers of type I, good enough. Number of viewers of type I seeing an ad from advertiser J. Good. And again, I is ranging from 1 to 3. J is ranging over A, B, C. Those are our decision variables. And again, before, when we were writing our decision variables, we wrote 9 of these decision variables, x1, x1b, x1c, x2, x2b, x3c, x3b, x3c. But now we have a compact way of writing our decision variables. Our decision variables are xij's, number of viewers of type I, seeing an ad from advertiser J, and I is ranging over 1, 2, 3, J is ranging over ABC. Okay, good. So now we're ready to write our optimization problem. Let's write our optimization problem. We're going to maximize our objective function. Good. Xij is the number of visitors of type I seeing an ad from advertiser J. Xij is the number of visitors of type I seeing an ad from advertiser J. Xij is the number of viewers of type I seeing an ad from advertiser J, number of visitors of type I seeing an ad from advertiser J. And from each one of those viewers, we make a revenue of Rij. So this product is the revenue that we collect from visitors of type I seeing an ad from advertiser J. Add over all visitor types, I is from 1 to 3. Add over all advertisers, J is over A to C. This is the total revenue we collect from all visitor types and from all the advertisers, which is what we're trying to maximize in the objective function. Okay. So this is a compact way of writing our objective function. Xij is the number of visitors of type I seeing an ad from advertiser J. And if a visitor of type I seeing an ad from advertiser J, we're making revenue of Rij. So this product is the revenue that we collect from visitors of type I seeing an ad from advertiser J. Add over all visitor types, add all advertisers. This is the revenue that we collect from all visitor types and from all advertisers, which is what we're trying to maximize. Good. So now, in the constraints, we're going to write a constraint that says the following. In the constraints, we're going to write a constraint that says the following. The number of visitors of type I, that are the number for each visitor type I, the number of visitors of type I that are seeing an ad from any of the advertisers should be no larger than the number of visitors of type I. Let's see it again. Let's see it again. For each visitor type I, the number of visitors of type I that are seeing an ad from any of the advertisers can be no larger than the visitors of type I coming into the system. Okay. So then XIA, visitors of type I seeing an ad from advertiser A. XIB is the visitors of type I seeing an ad from advertiser B. And XIC is the visitors of type I seeing an ad from advertiser C. Visitors of type I seeing an ad from advertiser A, visitors of type I seeing an ad from advertiser B, visitors of type I seeing an ad from advertiser C. So this sum is the visitors of type I seeing an ad from any of the advertisers. That should be no larger than the data number of visitors of type I, VI. And we have one of these constraints for every visitor type I that is ranging over 1, 2, 3. Okay. Good. So these constraints are saying that for each visitor type I, the total number of visitors of type I seeing an ad from any of the advertisers cannot be larger than the visitors of type I coming into the system. VI is my data here. And also we're going to write another constraint that says, we're also going to write another constraint that says, for each advertiser J, the total number of viewers of any type that this advertiser gets should be equal to the desired number of viewers for this advertiser. Okay, let's say it again. Let's say it again. For each advertiser J, the total number of viewers of any type that this advertiser gets should be equal to the desired number of viewers for this advertiser. So then, X1J is the number of viewers of type 1 that advertiser J is getting. X2J is the number of viewers of type 2 that advertiser J is getting. X3J is the number of viewers of type 3 that advertiser J is getting. So this is the number of visitors of type 1 advertiser J is getting, number of visitors of type 2 advertiser J is getting, number of visitors of type 3 advertiser J is getting. So this is the total number of visitors of any type that advertiser J is getting should be equal to the desired number of viewers by advertiser J. So that's the desired number of viewers by advertiser J. That's piece of my data. And we have this constraint for every advertiser J that is ranging over A, B, C. And lastly, all of our decision variables are non-negative. Xij is greater or equal to 0. I is ranging over 1, 2, 3. And J is ranging over A, B, C. Okay. So this is kind of a more compact way of writing the linear program that we wrote a second ago. We said for every viewer type I, for every visitor type I, the total number of visitors of type I seeing an ad from any of the advertisers should be no larger than the total number of visitors of type I coming into the system. And now for every advertiser J, we wrote a constraint. For every advertiser J, we wrote a constraint. The total number of visitors of any type, the total number of viewers of any type, that advertiser J is getting should be equal to the desired number of viewers by advertiser J. Okay, good. So now we can write these constraints in a little bit, in an even more compact fashion. In particular, let's look at this left-hand side of the first constraint. In the left-hand side of this first constraint, what are we doing? For fixed I, we're adding XIA, XIB, XIC. For fixed I, we're adding XIA, XYB, XIC. So then we can write the first constraint, we can write the left-hand side of the first constraint as, for fixed I, we're adding J from A to C. This is the left-hand side of the first constraint. For fixed I, we're adding XIA, XIB, XIC. So fixed I, we're adding XIJs over every J from A to C. So then we can write the first constraint as sum over XIJs added over all J from A to C is less than or equal to VI. This is a more compact way of, if you like, writing the first constraint. And likewise, we can write the second constraint in a more compact fashion. For fixed J, we're adding X1J, X2J, X3J. For fixed J, we're adding X1J, X2J, X3J. So then we're adding XIJs for fixed J. I is added over all. I is added over 1, 2, 3. For fixed j, I'm adding xij, I is ranging from 1 to 3. So it is setting x1j, x2j, x3j, and this is equal to dj. So this is a more compact way of writing the second constraint, if you like. So now let's just, to finish our work, let's write the most compact way of, let's write the most compact formulation of our linear program, if you like. Okay. Here's our objective function. The objective function doesn't change. We wrote it as compactly as we could. Overall visitor types, overall advertisers, revenue from a viewer of type 1 seeing an ad from advertiser J, and a number of viewers of type I seeing an ad from advertiser J. And the first constraint is saying, for each visitor type I, the total number of viewers that a visitor of type, the total number of ads that a viewer of type I sees over all the advertisers is going to be no more than the viewers of type I. The total number of ads that a viewer of type I sees over all the advertisers should be no larger than the viewers of type I. And we have this constraint for every I, 1, 2, 3. So it's taking care of our first constraint. And for the second constraint, we're going to write a constraint for every advertiser J, the total number of viewers that the advertiser J is getting over every visitor type should be equal to the desired number of viewers. And lastly, all of our decision variables are non-negative. Okay, good. For every visitor type I, we have one constraint that says for every visitor of type I, the total number of visitors of type I that are seeing an ad from any of the advertisers, for every visitor type I, the total number of visitors of type I that are seeing an ad from any of the advertisers cannot exceed the number of visitors of type I coming into the system. For every advertiser J, we have another constraint that says for every advertiser J, the total number of viewers of any type that advertiser J is getting should be equal to the desired number of viewers. Okay, good. So now when you have a formulation like this, instead of having 3 visitor types and 3 different advertisers, instead of having 3 different visitor types and 3 different advertisers, if you had 10 different visitor types and 10 different advertisers, this formulation would still stay the same. The only thing that would change would be the index sets, but the formulation would still be the same. We would have these constraints that says for every visitor type I, the total number of ads that that visitors of type I seeing from all of the advertisers should be no larger than the total number of viewers of type I. And for every advertiser J, the total number of viewers that advertiser J is getting from all the visitor types should be equal to the desired number of viewers by advertiser J. So no matter how many visitor types we had, no matter how many advertisers we had, this formulation would still stay the same. Only these index sets would be enlarged. Okay, good. So this is a compact way of writing a linear program. And you may be thinking about, when we formulated this problem, why did we put an equality constraint here? Why did we not put a greater than or equal to constraint here or anything else? And that depends on the business knowledge about the problem. So based on my business knowledge of the problem, let's say, in the business environment that I'm living, I have to exactly satisfy the desired number of viewers for each advertiser. But you may be dealing with a situation where you're allowed to give the advertisers more than they want. So in this case, this may be a greater than or equal to constraint that you say, I can satisfy the advertisers more than that they want. And if I satisfy the advertiser, if I give the advertisers more viewers than they want, from those viewers, I'm going to make extra money. If that is the business environment that you're living in, then you're going to formulate this constraint as a greater than or equal to constraint. Okay. So again, you may be thinking, why is this constraint equality constraint? Again, based on the knowledge of the business problem that I have, which again, we don't have access to the business problem here, but based on the knowledge of the business problem that I have, we're living in an environment where we have to give the advertisers exactly what they want. But you could have a business problem where you can give the advertisers more than what they want. In that case, this constraint would be a greater than equal to constraint. Okay, that depends on the knowledge of the business that you have. Okay, good. So let's try to stop here. So today we talked about what we mean by formulating an optimization problem. And that is specifying the decision variables, writing the objective function in terms of our decision variables, and writing our constraints. And we formulated optimization problems where the objective function and the constraints are all linear functions of the decision variables. And those kinds of optimization problems are called linear programs. Throughout this course, we're mostly going to focus on linear programs. When we solve a linear program, the optimal solution can be a fractional number. At the very end of this class, we're going to talk about integer programs where some of the decision variables are restricted to be integers. But for the most part of this lecture, we're going to be talking about linear programs. We're going to be talking about linear programs where the decision variables may take fraction values in an optimal solution. That's something we're going to have to live with. And we saw how to use Excel's linear programming solver. And also we saw how we can formulate linear programs in compact fashion. And writing linear programs in compact fashion is going to be very handy, of course, when we're dealing with linear programs with many, many decision variables and many, many constraints. Good. So let's stop here.